Okay, that should work.
So I'll kick off the recording. You all are seeing the document, right? Okay. I hope. I'm sharing this, in other words. This. Okay. Okay, so I'm going to kind of, last time I kind of started in with this theoretical thing, and we got to Chalk Engine at the end. And actually, where did we leave it? But I'm probably going to start over Chalk Engine a little bit, because it never hurts to say things twice. Right, okay, I see. And then we'll go quickly over those basics and then go into a little more depth. And one of the things I would like to get to, if we get as far as I want, we'll see. We'll talk a little bit about delaying and some of the other subtle stuff, which Chalk Engine doesn't totally do correctly right now, I realize. But so the high level idea. So we've got, last time we talked about how the Chalk engine is basically contains, when you create it up, it has a bunch of what are called tables. And a table is basically the current state of solving for some goal, where a goal is basically, well, that seems a little circular, but the goal contains an environment. I guess I can say it like this, right? Where a goal has an environment and this sort of, I need a better name than goal. Let's call it query, for some query, trait query, where a query is an environment and a goal. And a goal is something like, no emojis, something like either what we call a domain goal, which might be like basically a predicate like implemented T trait, or all these kind of meta goals like that two goals have to hold, or that if you assume this clause is true, then we can prove that goal, these sort of things, right? And the reason that we actually call it domain goals is that the logic for these kind of combinators here is actually built into the engine. But the logic for domain goals is supplied by a callback. So essentially, no matter what kind of domain this Chalk engine is applied to, and works the same. To solve two goals, you solve first the one and then the other. But the specifics of what rules exist for a given domain goal will vary, right? So there's a callback for domain goals that gives up basically to solve this goal G in that environment E. Here are the options, and this is the work in Chalk number 216 that Detrumi was doing, or Lucas, I think. Non-usernames, was basically implementing that callback in Chalk Solve. Because previously it only existed, well, the callback existed, but in a very simple form. And the name table comes from this term called tabling. And I actually thought it might be useful to talk a little bit about how a traditional Prolog solver works, because I remember there being some questions in it, and I thought it might elucidate where the name comes from. I'm not going to spend a lot of time on it, but it'll also be important later on, I think. Like if you have a traditional solver and it has some goal like, I don't know, something like this. This would be something that is kind of true. Let's add a few more things. The way this solver would traditionally work is it would go in a depth first. It doesn't have any, Prolog solvers didn't have any like heap data structures. They're purely stack based. And what they would do is they would solve it by if you started them off with what is the answer to foo of x, they would find a rule and just depth first search, try to enumerate out ways that rule could be true. So first it would go into bar, right, and say, okay, let's solve bar of x. And then it would go through these rules and say, aha, well, here's one way bar of x can be true. If x is 11, right? And then it would kind of pop back and say, okay, if we know, now we have a solution for bar of x, let's look at baz of x. And so now we know x is 11, so we would search for baz of 11. This would fail because there is no rule for baz of 11. And then it would come, kind of pop back on the stack to like, okay, well, that failed. So what were we doing before that? Oh, we were solving bar of x. And there, oh, look, there's another answer. X is 22. Let's try baz of 22. This succeeds. Now we have a full answer. And we can kind of propagate this answer out, right? So everything was maintained on a stack. There's a little bit of complexity because of the need for, but I kind of didn't show you some of the more complex examples where you might have a need to keep things on the stack for a little longer. But, well, no, not really that, actually. I don't think prolog solvers in their traditional form ever kept things in the stack. But they would just have to need to save checkpoints and restore as they search. But they could wind up doing quite a lot of work. And there was one particular problem that is really hard to solve unless you have tables, which would be if you have, let's see, what's the usual setup? It would basically be if you have a recursion, if you have a left recursive setup. This is a very naive one. This would be an infinite loop for a prolog solver, because what it would do is it would say, I have to solve foo of x. Well, let me solve foo of x, and that pushes another thing on the stack. So just like a function calling itself, it's going to recurse forever for a traditional prolog solver. And what tables basically would do is try to add to this. So let's me extend this example. So if we had this set of rules, there's only one real answer here, which is x must be 22. So if I ask, like, what are all the x's for which foo of x is true, it has to be 22, because at least if x is inductive, because this kind of is an infinite loop, right? There's no answer coming out of here that the only answer that you would have would be an infinite proof tree that's like, you could sort of, it would never terminate. But if x is, but on this option, we can prove that bar of 22 is true right there, and therefore foo of x is true. So we have a little sort of proof for that. There's only really one possible answer. X is 22, but as I said, a traditional prolog solver will actually just loop forever instead of giving us that answer, because it gets stuck here. And so what you would do with tables is that you would, a tabling solver would basically say, when there's a recursion, I'm going to stop and then go look at other avenues. So then we would come up with this answer for x equals 22. And then we'll come back and try again. And let me see if I can explain it. So we would say that we would start going down foo of x. We find out, oh, well, this, let's make it. Just add. Actually, I'm going to stop this. I'm realizing I'm going way down into how tabling works, and it's kind of not that important, because this is how the we'll sort of see it through the way a chalk engine does it. This is a little different, but basically there's this version of prolog solvers called tabling, and the idea was that they added a side table of answers and they handled recursion more elegantly, which is exactly what the chalk engine is doing. So I'm going to come back to this example, but let's dig more into the tables. So right, so a chalk engine table consists of the goal we're trying to solve, or the query rather, which is a goal, an environment in the goal. And it consists of a set of answers, and it consists of a set of strands. And each strand is the possible way to find an answer that we haven't figured out yet if it yields a new answer or not. Right? And what a strand, the state of a strand. So the idea would be then that what we're going to do when we want to evaluate a given table, we can look and see what are the answers we've found so far, and if the answer we're looking for isn't in there, or if we maybe want more answers, we can go look and see if there are any strands to pull on that can possibly yield up new answers until we run out of strands. And then we know that we've got all the possible answers to this particular query. That part makes sense. So the state of a strand is what we called an X clause in the other day, and it basically consists of a substitution. So let's look a little bit at this goal. Uh-oh. GitHub, rustling, chalk. No, strand is in here. So if we're trying to solve, let's say as an example, it's a good example. If we had some rules like, I'll give my favorite example. We have vec of t is clone if t is clone, and we have clone of u size. And suppose we were trying to solve the query sort of this. So what this means is find me all the types that are clone, right? And in that case, our table would be instantiated with clone. And here I'm going to use I'm using this $0 because the idea is this is a canonical goal, which means we've renumbered or sort of renamed all the variables in a canonical ordering, and I'm going to give them numbers to make that clear. I think before I used letters of the alphabet. So the idea would be that these, what's the difference? I'll do it. I think it's the convention I did before. I'll be consistent. We're trying to solve for some variable t, and when we have our table goal, we're going to renumber it so that they always start with a, right? So that they're the same whenever we come and do it again. Yeah, and the substitution then that is being carried along in a strand would be like the current value for $a, right? And along with any other variables that might appear in this table's original goal. So the substitution has the current values for all the variables in the goal, in the environment/goal.
To start out, would that just be the identity, not the variable to itself?
Yes. That's exactly right. So you might have something like it's a little bit, there's a kind of a namespacing thing going on here that's a little confusing the way I'm writing it. Maybe there's a better notation. What it would be is that the left-hand side of this is, so maybe I will use the numbers after all, I don't know, but is basically naming variables from the canonical, like by their canonical index, right? But the right-hand side of this, while we're solving, we sort of create an inference context, and those names are expressed in terms of that inference context. And it so happens that initially, the first variables we're going to make in our inference context have like a one-to-one relationship with the canonical variables, so they're sort of identity. But that's not required, right? And if you made the variables in a different order, that would be fine. In which case, so basically this is expressing some variable in terms of our current inference context, and this is the goal itself.
Okay.
And so the straight has this substitution. What else does it have? Let's try to get it right. Right, the X clause. And yeah, so one thing I realized I didn't fully explain before. So it has the X clause, which basically contains the delay set, which I'm going to ignore for the moment, and the sub-goals we have yet to prove. But there's one other important thing, which has a selected sub-goal. And the idea here is the sub-goals we have yet, basically that the strand can be in one of two states. It can either not yet have started searching through a particular sub-goal for answers, or it can have started, in which case it's waiting. And that's what this selected sub-goal is distinguishing. So if we come back to our example, let's say we were trying to solving clone of question mark t. We would, to start, we would create a table, because in the very beginning we don't have any tables yet, right? So we're going to create a table for clone of question mark t and create the initial set of strands. And to do that, we're going to use our callback to figure out the way to solve the domain goal. So the thing is, we're solving a domain goal, clone of t, and we don't know what the ways are to solve domain goals. So we use the callback, and it will tell us there are two possibilities. Either, these two. I'll just call them program clause 1 and program clause 2. So we're going to make two strands. One for program clause 2 and one for program clause 1. All right, so let's see. So strand 1 would look like the substitution at the moment is going to be empty, or identity rather. So what I'm going to do is I'm going to make, just to make it a little clearer, to help, I'm going to create a variable name. So, let's see. Substitution might be like question mark a equals question mark t, or question mark x, let's say. Right, and then the X clause would be if we're doing this rule, we basically have a sub-goal list of clone of question mark x. And this isn't quite right. I'm sorry. So looking at this goal, the first thing we see is we have vec of t in here. Right? And so we know we're trying to solve, this should be a, trying to solve clone of question mark a. We have this rule for how to prove it. So we have to unify vec of t. We have to kind of instantiate. So strand 1 is going to be, I'm going to write it here, clone of vec of t if clone of t, right? So we instantiate t with a variable. Let's call it question mark x. We unify vec of t. We unify our goal from the table, which is clone of question mark a, with the goal we were given, which is clone of vec of question mark x. And this gets us a substitution, which is, so far we figured out the question mark a, like in this strand, question mark a must be vec of question mark x for some x. But we have this sub-goal list of stuff, sort of the right-hand side of this program clause. And we have a no selected sub-goal at all. Does that make sense? Where we got strand 1 from. And strand 2 is somehow simpler. This would instantiate, there's no t. And strand 2 would just clone our goal with clone of usize. So we get question mark a must be usize and a selected sub-goal list that is empty. And that's our state before we've actually done anything. All we've done is create the table and set up the strands. And so the next thing we would do then is to say, we can actually try to get an answer from the table. So what we do then is we try to say, we do this thing called ensure answer table 0. And what it's going to say is, it says, give me the answer 0 with number 0 if it already exists. And if it doesn't, go try to find answer 0. And the reason we have the index is so that sometimes they're like recursively pulling answers from themselves, as we'll see. And so what we will do here is we will say, okay, we have no answer 0 yet. So what we're going to do is we're going to pick a strand to see if we can find a new answer. So we'll pick strand 1. Let's say it's strand 1. What happens with strand 1 then is the current state is it does not have a selected subgoal. So when you're in a strand, what you want to do is you always want to either you have nothing left to prove, or else like the subgoal list is empty, in which case you're an answer, or you have to select one of those subgoals and start drawing answers from it. So in this case, there's only one to choose. So we'll select the subgoal clone question mark x. And we will fetch its table, but we'll find, now this is where it gets tricky, is that this is actually the same table we started with. Right, so what we'll find is that it's already on the stack. Now, what stack am I talking about? Well, when we went to ensure an answer, we actually have a stack of all the things. The work of ensuring answer 0 gets pushed on the stack. And now I want to look at the code. I'm realizing why it's better to prepare. I feel a little bit like I'm throwing things out in random order, so let me know what is making or not making sense, please. Take your silence as it's all perfect, or it's so far gone. Right, okay. So what happens when we find a cycle is that we know that this strand of inquiry cannot make further progress right now, because it would have to it's in a cycle. And but what might happen is, so the problem we got into was, in order to solve clone of vec of t, we had to solve clone of t, but that kind of required us to solve what we were already solving, so we're a little bit stuck. But it could happen that we could find answers through another route, right? In particular, this one. So what we do in the event where it's already on the stack is we're going to pause this strand, basically. And I'm going to show exactly how this works in the code, but I'm trying to give a high-level feeling. We're going to pause this strand and pop back up until we get to the head of the cycle. So in this case, that's not really anywhere because we only have one table. But it could be that table 0 has invoked table 1, invoked table 2, and now we got to cycle back to table 0, in which case we're going to kind of pause on the way up. And when we get back to table 1, we'll say, okay, we tried strand 1, it got into a cycle. Let's put it on the side and try strand 2 next and see if it gives us any answers. So we're going to collect strand 1 into a vector of cyclic strands and try strand 2. And in that case, strand 2 has no subgoals at all. So that means that we're basically done. So in the case of strand 2, we'll say no subgoals. This is an answer. So we'll add it to our answer list. And we're going to return. So the current state now of the table is that it has an answer, which is question mark a equals usize. And it has, actually, I think the way that the solver works, it would actually have an empty list of strands at this exact moment. And that's because we took this other strand and we put it in we're holding it to the side at the moment. So it's not in the table, it's in this list of cycles. And then when we return back out, to this point of ensuring the answer, we're going to say, okay, we found an answer 0. Let's take those strands that were cyclic and we'll put them back in the table now, because it might be that we tried them before we had an answer 0 and we hit a cycle, right? But maybe now that there is an answer 0, they will actually be useful. So we'll put them back in the table. So we're going to add strand 1 back into the table. And that's where we leave this first sort of round, is that we have a table which is solving, which is for clone of question mark a. It has an answer list, which is exactly 1. And it has a strand. There's still another way to derive more answers, which is maybe, which is this sort of like, maybe question mark a is vec of question mark x, but then we have to prove clone of question mark x.
So when do we check that vector of cyclic strands?
When do we check that it's, what do we do with this vector of cyclic strands? Is that the question?
Yeah, at which point do we actually check it?
So in this case, we're going to add the cyclic strands back into the table because we found an answer. I'm not sure what you mean by check it. Like, how did we determine that it was a cycle in the first place?
No, when do we pop it out again?
Okay, I see. That would be the next thing I'm gonna, we don't, basically, not so far, because we found our first answer, and all we were asked for was one answer, and we found it. So the whole thing operates always on a like per answer basis. But if the caller then comes back and says, okay, like if someone were to call and say, give me answer 0 again, we would just give them usize. But if they call and say, okay, I got that usize, but I'm curious, is there another answer for this particular query? Now is when we're going to pop this strand back out again, because now we'll say, well, we don't have an answer 1 so far, but we still have ways to make new answers. So let's pop out this strand, right? And actually, I left one little bit incomplete. So here, this is the in the current state of the strand, this is the substitution, and this is the list of subgoals. But there was also this selected subgoal, right? And what that actually looks like is going to be, where is it? It's probably under strand. Selected subgoal. Right. So it's actually a pair. Well, it's a couple things, but the most interesting one is this. So this is the index in our list of subgoals, but this is the this is the index in the list of answers for that goal. So if we come back here, I sort of glossed over this. I said we're going to select the subgoal clone of question mark x, right? And what that means is our selected subgoal value is going to be essentially a pair. The actual data structure has a few more things, but that's sort of for efficiency. Where we're saying, we're saying we're in the process of iterating through all the answers of this subgoal that there are, because for any answer to that, our rule gets solved, and we're currently at answer 0. And so when we come back, now we're going to pop off what we called strand 1 from the list of strands and activate it. And we already have a selected subgoal. So we're going to go to the selected subgoal, which is this one, clone of this, and ask the table for answer 0, right? So we're going to go and say, okay, for clone of, if we canonicalize clone of question mark x, we get this table that which we also called table. What is the first answer in that table? Does it have a 0th answer? And the answer is that it does. It's U size. So in this case, now that we have an actual answer, we're not going to get back a cycle anymore. We get back question mark x equals U size, basically, which is answer 0. And so we actually succeed. We produce a new answer. But we'll come back to that. But does that make sense? Before I go further, how that cycle winds up playing out?
So it's essentially not a cycle if you already have an answer, or
right,
circular.
So this is, yes. It's kind of like, the question is basically, is there some finite way you could arrange the rules such that you would find an answer, if you think about it? And like, maybe I think it might be helpful. I find it helpful anyway, to try to arrange them to try to show what I'm saying. So like, here are 2 rules. Let's call them rule 1, or no, yeah, I already gave them names. And so the question is like, we can show that U size is an answer because we just have, I don't know which notation to use. I'll use this one. Because basically rule 2 just applies, right? But we could show that vec of U size is an answer because we can use rule 1 and then we can use rule 2 down here on the T, right? So like, we produced an answer from 2, which was U size. We kind of passed it up to here to get the value of T, and that gave us an answer here, which we kind of passed up to here to get the full answer. But we could show, indeed, we can build on that and show like that vec of U size is an answer, because we just sort of add another instantiation where we use rule 1 twice and then we used rule 2. and actually there's an infinite set of answers we could show this way. So that's what we're kind of trying to do, is find these tables, these stacks of answers. And it kind of, I should recall that our query always was this. So it kind of makes sense that we're getting an infinite chain, because I asked you to tell me all, like, what are all the clonable types? That's what this query is saying. Go ahead and give me all the clonable types, and there's an infinite set, right? But so that's what this is doing. And basically, each time you have an answer in the table, this is something that we found where we reached an endpoint. And then we can build off it. Further future strands can build off of that answer. So kind of makes sense? Not at all. I should keep talking about this. All right. So what I wanted to do was, we didn't actually follow. There's one last part of what happens here. I'm thinking that maybe, I'm wondering if, okay, I'll keep going, but I'm wondering about if I can draw a picture of some kind. So basically what happens here is, when we do find an answer, what we do is we do two things. We split the strand into two possibilities, one of which uses the answer we found, and one of which looks for a next answer. So when we get back from this second round, we're going to have a table in this state. I'm just going to show you the end state because it's easier. So what we're going to do is, the second, when we ask to ensure answer 1, we're going to pick off this strand. As I said, we're going to ask for, it's interested in answer 0, and now there is an answer 0. So we have a result, but that may not be the final answer. Like, there could be more answers to be found, right? There's Vec. We found only the first answer from this sub-goal. There might be more sub-goal answers it can produce. So we're going to push this another strand, basically, which has the same, except this time it increments the counter. And it says, we're looking for sub-goal number 1 this time, because we already found sub-goal number 0. And then we can go on with our own life, right? So our current strand, after we find an answer, we get to discard that sub-goal. So we wind up with something like question mark A equals vec of usize if empty list, essentially, which is an answer. Right, so that's how we get to this answer, was because once we got an answer for this sub-goal, now we have no more sub-goals left. We're all done. But we still have a strand left, because part of processing the answer was to push a new strand with the next answer index. And so that's how we will wind up with this infinite list of answers. If we keep asking for more answers, we'll just keep getting more. But what would ideally happen, this particular setup, what will happen is that we'll stop from the outside asking for more answers, because we'll see that we're just producing an infinite, too many. Like, this particular query doesn't give us any unique value for A. After 2 answers, we can see that. And so we can stop, because usize and vec of usize are like not the same type. So I think the thing that I'm trying to get across, and I'm not sure if it's succeeding, is that the way that this solver works at the highest level is that you are, for any given query, it is producing answers that are getting fed into other queries. And so when we select a subgoal, we basically start saying that for each answer of this subgoal, I can further process that answer and it might produce an answer to myself. So that's what's happening here is we're saying go through all the answers of clone of X, and for each of them, one of my answers, like I'll produce an answer called vec of X. Okay, I did not get to the material, but I feel that I feel I've reached a stopping point of some kind. I'm trying to think what's the best way to proceed. Perhaps the second example, or perhaps come back to this again next week with a different thought or a different set of examples. Let me ask you this. Which things, like, I don't know, what is most confusing of what I said or most makes sense?
Yeah, I've read your blog posts on this, so for me it was kind of more of a read since I worked in Chalk.
Maybe I'm starting to.
I've been able to follow it.
Okay, well, that's encouraging.
Yeah, it's making sense now.
All right, so then let me show. Well, let me go a little bit into the problem that I'm trying to solve with the non-enumerable clauses in that case. So one of the problems would be if you had a rule like this. Well, first of all, first problem is this, right? If you have, I'm just going to keep it kind of abstract, but I'm going to use one sort of Rust trait. Let's suppose I had a setup like this, right, which might come from like impl for all t, foo for t, where t bar or something. Then there's two traits here, or two subgoals. If I were going to try to enumerate the types A that work, there's two subgoals I could start with, and it matters a lot which one I start with because maybe like there's exactly one answer for bar of A, and it's U32. So if I start with that one, I'm going to produce an answer from the bar of U30, from the bar of A table that's going to be U32, and then I'm going to, if I start, so we'll start out as foo of question mark A, sized of question mark A, bar of question mark A. If I select bar of question mark A, I might get question mark A is U32 as an answer, right? And then my current state will be foo of U32 if sized of U32. And if I select sized, I'll look up a table for sized of U32, which is a very narrow query. There's exactly one type, and it'll come back true, right? Or whatever. It'll come back with an answer, which is an empty substitution, which is true. But if I were to select sized of question mark A instead, now I would look up a table for sized of question mark A, and that's kind of every type that exists, right? Not every type literally, but almost every Rust type is sized. So that's an awful lot of types. And what I would wind up doing is kind of searching through them and testing, is this type bar? Is this type bar? Is this type bar? So like, let's say it might yield up, I32. And then I would say, okay, now I have foo of I32 with bar of I32. And so I can look up a table for bar of I32. That's going to be false. Okay, then it might yield up string, and so on, right? And eventually it's going to give me U32, and I'm gonna find that answer. So it's gonna, in theory, work either way. It doesn't really matter which one we choose, but in practice, it actually matters, of course, quite a lot, right? And one simple way to solve this is don't pick size, right? So we can, this is what I'm saying, we have a hook that Keith added that's like, within a sub-goal, be a little more selective about which thing you pick first. Right now, we always pick randomly, basically, depending on the order in which they're listed, just like Prolog would do. That's not so smart. It might be better to pick, we could be smarter about it, but that's not a real solution, because we might be sort of hidden. Like it might be foo of question mark a if bar of question mark a, and baz of question mark a, and bar of question mark a if sized, or let's say baz and bar of U32. So bar didn't change here, but foo did. And the only thing I changed about foo is that instead of saying it has to be sized, I said it has to be baz, and baz is true if sized, right? But now, it's not so easy for me to know which one I should order. I could use some heuristics perhaps, but like it might be that basically in general it's going to be hard for us to do that, because we kind of get locked into the ordering. We have to process the way that the current system is set up. Basically, in order to find answers for baz, I have to process all of its sub-goals before any of those answers can propagate back to foo and then be fed to bar, right? Or vice versa. So basically, foo has to pick one thing that's going to produce answers completely and go to baz and process, and then filter those answers through baz and through other predicates. So that's the way I think of it anyway, is that there's kind of the sub-goal we select is going to wind up being the producer, and all the other sub-goals that we didn't select are kind of consuming those answers one by one. And so we really want to be able to reorder things in a more flexible way. And it turns out there's already a mechanism for this that I've been sort of ignoring each time we hit it in the solver, called delayed literals. And they're there for another reason. But I think they're actually not a bad, they potentially apply to this problem too. And what they basically let you do is to say, when you get back an answer, it includes not only a substitution, but a delayed literal set. And the delayed literal is basically like modulo, right? So you can kind of say, like, well, in the case of baz of A, we could say baz of, let's say baz of A is true. I think how to write this. So this pipe, the stuff before the pipe is the delayed literal, right? And what this is basically saying is baz is true for any question mark A if question mark A is sized. Now that's essentially, this is such a simple example, it's kind of pointless, but that's kind of restating the rule that we already had. But the point is we just deferred the work of figuring out whether A was sized or not. And we said, no, here's an answer. You can go take this answer and try to solve bar with it. And then once you're done with that, maybe you'll come back and solve this sized problem. So that's, in a nutshell, what I think we want to be using for these sorts of problems, is allowing us to say, when we get to the point where we would have to enumerate the program clauses for a given goal, and thus create a whole bunch of strands, we might instead say, you know what, I can't, this is a non-enumerable goal, like I can't come up with a bunch of strands for it, but what you can do is delay it. And in that case, we would add it as a delayed literal and propagate it out, and then we'll kind of revisit it once we know more type information. So in the case of this solver, if we selected Baz first, bad luck, but it doesn't really matter because it'll just produce one answer, which is basically a no-op. It gets fed to bar. Bar will solve, find that A is U32, and then we'll come back and look at this delayed literal and say, well, now it's not sized of A, or it's still sized of A, but A is U32, so that's actually pretty easy for us to solve. That's the high-level idea. And these delayed things can propagate through however many levels of the tables that they need. So idea, roughly, is when you have program clauses, you can instead declare the goal non-enumerable. But what's a little bit, or what's worth maybe, well, the question is raised by this, let me put it this way, is when do you stop delaying if you have a delayed goal? How long do you delay it for? At what point do we sort of undelay it? And it's maybe worth talking a little bit about the real purpose of delayed literals, or the original purpose, I should say. And I was reading into this before this talk because I was trying to remember what exactly, trying to remember the details. And it's interesting. So the reason that they're around has to do with negative reasoning and some of the weird scenarios negative reasoning can get you. So here's a set of rules. This is like the lazy Prolog person's. Here, P and Q are basically predicates, like nullary predicates. So it might be clearer to say, at least I find it a little confusing. So I'm going to add in these pointless variables to say P of X is, there's one rule for proving P of X to be true, and that's if Q of X is false. And there's one rule for proving Q of X to be true, and that's if P of X is false. And this is not exactly a contradiction, but it has some funny properties if you have this setup. This is called a negative cycle, where there's negative reasoning going between them. And that is that, like, they can't both be true, clearly, but they also can't both be false, because let's say if P of X is false, well then Q of X must be true, right? Because we can prove that it's true because not P of X is true, and vice versa. And so their results are sort of linked. What you kind of have is an XOR. Either you can sort of say P is true, but you don't have any reason. There's no rule that you can use to show that P is true. But if you just sort of said that P were true, it would be consistent then with that Q of X would be false and vice versa. And so that's kind of a problem for our formulation, because we would like to be able to ask a query and get back, like just ask one query, like is P true, and get back a definitive answer. But here it turns out to be sort of linked in such a way that it could be true or it could be false, but it depends on what answer you give to this other query, Q of X, that's independent. So the answer that we end up with is actually ambiguous. And this is where there's this thing called the Well-Founded Semantics, or WFS, which basically says, it's kind of a definition for what does truth mean. And it comes up with 3 results for any given predicate: true, false, or ambiguous. And the idea is something is true if you can kind of go back to this, if there's some finite little tree that will show that it's true from the rules, and something is false if there exists no such trees. But an ambiguous result kind of comes up in scenarios like this, where there's negative cycles that cause it to either be true or be false, in this weird way. And there's another kind of thing, which is not really relevant here, called answer set programming, which allows you is a different way of, it's a different semantics for what true and false means, and it would actually give you 2 answers here. It kind of, the reason it's called answer set is it doesn't give you an answer to is P true or not. It gives you a set of answers, and thus it can handle things like true, false, and false, true, because there's going to have those are linked, and it can give you all the answers at once. Whereas the well-founded semantics is more narrow. But anyway, we want this one. But it turns out that in order to actually compute the answers to this, you kind of have to have the same concept of delaying, because what winds up happening, the way that you solve the negative literal like this is to make a table in forest chalk engine terms, and see if there's any answers in it, basically. And so what would happen here is, in order to solve P, we would put Q on the stack and then sort of put it in a negative way. And in order to solve Q, we would try to put P on the stack, and we would get a cycle. And if we just treated it, and what we basically have to do is defer that cycle and wait until we fully compute all the other possible strands for Q and P. And if at the end of this, all we're left with is this one sort of delayed literal like this, we can either, how can I say this? If at the end of all the strands, right, if all we're left with at the end, we have these strands and they're all cycles, it's all the things that are left, then if there's no negative with them, basically they're all just false. There are no answers. And if there is, then it's ambiguous. Let me try to give you an example. I realize that's kind of confusing, but because I'm confused, that's why. But basically what we do is, or negative cycles require us to reorder the evaluation and delay. So yeah, I have to look up and have a crisp example for exactly why this is, but it's basically similar to this scenario I was trying to paint here, where you kind of can't locally figure out when you have negative cycles what the answer is. So what you want to do is delay, let the answers propagate through the rest of the system fully, and then come back after that's all done, and you've gotten all the answers that you can get through that means, and then you can kind of work out whether the delayed literals were true or not at the end of the day.
So you try to avoid delaying the literal by, saving off this cyclical answer like we did before and going through the other strands. But then if there are no other strands that can give you an answer, then you go ahead and delay the literal. Is that accurate?
Actually, in that case, no, that's not quite accurate. Yeah, I didn't really cover a case with delayed literals, but what would happen in that case, I didn't cover what happens if you don't get an answer. When you do encounter a cycle, that was a positive cycle in particular. So, and when you encounter positive cycles, you can put the strand to the side and see if you can find any more answers. And then if you can't, you can basically just throw the strands away, because they have to correspond to like a foo of t if foo of t situation that would never have a finite size. Because in order for them to have a finite size, there must be some other answer for them to build on, basically, that was found some other way, not through that strand. But what happens is when you get a negative cycle, then you don't consider that to be a cycle. Instead, you delay the literal. Instead, you move the negative edge into the delay set and call it a regular answer. And the reason for that is what I don't have crispy on the tip of my tongue, but it comes down to this, that basically you wouldn't, it would be wrong. I guess it would be like P of X if not. Maybe we can even make an example of it. Here's an example, okay, that's a little weird, but one thing, it's a very simple one, but one thing to note is that this is not a problem. So here we're saying one way for p of x to be true is for it to be false. But another way is that it could just be true. And that's okay. It's like two ways for it to be true. And this one is obviously a bit of a contradiction. So that's not a very useful rule. But what happened is that you would, when you encounter this negative cycle, if memory serves, you would basically, instead of calling out a cycle of the normal kind, you would delay the p of x literal and call it an answer. So it would be like p of x is true as long as p of x is false. And then you would go produce a second answer here. And I'm trying to remember why. Yeah, I don't exactly have it on tip of my tongue why, but there's a reason for this.
Okay, so when you encounter a cycle, it depends, how you handle it depends on whether it's a positive or a negative cycle.
Yeah, let's take a look at the actual code. So it's worth asking, why does Rust even care about this negative stuff, actually? We don't, as it happens, we don't have negative reasoning in Rust. And all of these complexities are a good reason not to add negative reasoning to Rust. What we do use it is in exactly one place, which is coherence. Where if you look at what the coherence rules are really saying, they're basically saying you're allowed to add an impl if there could never be a downstream impl, that, or something like this, if there is no upstream impl that conflicts with it, and things like that. And so we use it in a kind of limited way. And interestingly, the way we use it, it could never form a negative cycle, because it's basically only at a top level rule, and that rule never recurses and asks for other rules that could have negative in them. So maybe none of this matters, and it's possible that I've been tempted to just rip out all this logic, or at least I think it would make sense to sort of special case this delaying logic to the problem we actually have, which is the size problem, and not to this negative. But then I thought, I don't know, it'd be nice if maybe we will add negative. So anyway, but you can kind of see what happens here if you, let's see. So walk through maybe I'll walk through the code just a little bit. I don't know if we did this before, but so this function pursue next strand, this is what actually starts a strand. The strands are kept in canonical form when they're not active. That's because in Rust C, you can't have an inference context that lives longer than a stack frame. And the inactive, like the table, when all the work is, once we've produced an answer, all the stack frames that are processing a strand have to pop off. So all the strands that are not active have to go always in canonical form, so they don't have any inference pieces, and they kind of get rehydrated afterwards. It's an annoying detail, but that's what's going on here. And then once we've rehydrated it and created, we call this pursue strand, which picks a subgoal, gets the table, and then, right, and then you see here that there's basically two options. The subgoal can either be positive or it can be negative. And if it's positive, we try to get the answer out. And if we got an answer, great. Otherwise, if it's a cycle, what we're going to do here is we're going to propagate back an error result. And we are also propagating back the canonical. We're basically putting this, we canonicalize the strand and we put it off into the error, and it's going to get pushed back up the stack through the result value and eventually processed. And we'll find that in a second. And there's a few other possibilities here. It could be that we asked for answer number 1 or whatever, answer number I, and there were no more strands to pursue. In that case, we know that there will never be an answer number I, and we can give back no more solutions, in which case this just fails. This strand itself, like this strand dies because that subgoal is not solvable, or has no more solutions. And the quantum thing, I forget exactly. That's something else I wanted to look at, but I think there are times when there are various points here where we sort of pop back, and that's what it is. So like when we process one of these answers, like here we said, okay, we'll go down strand 1 and we'll put it on the shelf now because we got a cycle, and we'll come back and process strand 2 and stuff like that. And I forget exactly where, but there are some places where we kind of we return what we call quantum exceeded, where we don't want to just keep searching forever. So if we spent enough time looking in this strand, we return back a sort of ambiguous result saying like, come back again later, and we'll keep going. But this way we can, because we want to ensure that we search the stack space more thoroughly. So there are places where we could have kept going if we wanted to, but because we don't want to be depth first search, we don't. That's what quantum exceeded is about. And in that case, all it does is it just pushes the strand back on the table for later and returns. So you can see that the strand is like a owned value that gets pulled out of the table, lives on the stack for a while, and then either gets put back into the table, or if it doesn't get put back in the table, like this case where we just return an error, that means it's dead. There couldn't be any more answers coming out of it. Or it gets turned into an answer, and that's good. And the co-inductive case, we'll come back to that. That's actually where there's a bug. And a bug where delayed literals would also be a solution. So now I'm just a little bit curious because I don't remember. Right, so somewhere here, this is where we process and we accumulate the cyclic strands into a vector and so on. But that's the positive way. And if you look at the negative one, if it has if there is an answer, if there's an unconditional answer, then we know that the negative thing is false. Like not P is false if P has an answer. So we fail. Similarly, if there are no more answers, that's good, we succeeded. But if we get cycles and so on, then, yeah, okay. I guess we wind up doing the same thing, but if we go up with this minimums, the point of this minimums code here is it's tracking how far up the stack was this cycle. And you see that there's like a positive and a negative saying like, we had a thing on the stack. The positive is how far up the stack did we have a positive backup dependency, and how far up the stack did we have a negative dependency. And this is used to figure out if we should delay and other stuff like that. So the treatment of positive and negative is different. And let me just, well, there's a bug that's related to, so we have this, I've been talking about how all the solutions have to have a finite size for their tree. I think I'm going to stop here, actually. I'm looking at the time and realizing this is like well over an hour. But we should talk about the co-induction bug. The TLDR is that we don't do it right. But it's the same kind of thing where what we wind up doing is we inappropriately, basically co-induction means cycles are okay. It's the short version. And we decide that a cycle is okay, so we treat it like a successful answer. But actually, that might be a little premature. So if you had like this, if this were all the rules you had, and foo is co-inductive, let's start with this example. If foo is co-inductive, then this means foo of x holds for any x. So unlike the inductive case where this would hold for nothing because there's no finite tree, it's actually fine in this co-inductive logic rules, if not very interesting. But if you added in this bar, because there's no rules for bar, this is basically still false, right? We can't prove foo for any x because we can't prove bar for any x, and we have to prove both foo and bar. But our logic will say that it's can give the wrong answer, maybe not in this simple of an example, but with a few more levels, because we would sort of incorrectly decide, oh, this recursive thing is true. This is true because it's already on the stack, so it's a cycle, so it's true. But we don't realize that we will later disprove it through bar. And that can lead us to false things. And I think the answer would be, when we see these cycles, instead of just saying it's true, we should delay and say, foo of x is true if foo of x is true, and propagate that back as far as we have to. So delayed literals where it's at, I guess. It's the short version of this. All right. We'll stop. We'll talk more about delayed literals next time. Maybe I'll try to figure out exactly what's going on with the well-formed semantics, although I don't know how relevant it is. But sound good? I think we're getting to the point where I have nothing left to explain, and it's more like we should talk about how to actually solve it. But
Sounds good.
all right.
Thanks.
Thanks, y'all.
Yeah, thanks.
See you later.